Hello and welcome. This is Physics 313, Chapter 1, Section 3. And in this section, we start to make things a little bit more mathematical by introducing coordinate systems and also vectors. And so looking back at the first couple sections, we defined, in Section 1, we defined what a motion diagram is, just overlaying an image of an object moving, overlaying it on a specific spot several times and seeing if it's speeding up, slowing down, or going constant speed. And then we introduced the particle model, saying that, well, let's, to get a reasonable answer for these objects, let's just ignore all the features of the object and just consider a dot on the object. Now we want to add a coordinate system to it. And so what are the things that a coordinate system needs? Well, the first thing a coordinate system needs is an origin. And obviously that's the location where we define our zero. It also needs a direction of positivity for each of the coordinates. So you see on this picture right here of you can read the notes here. On this picture, this motion diagram for an object sliding down a hill, right? The coordinate system, we have our well-defined origin, our zero, and we also have the directions of positivity. This book will always denote to the right as positive and up as positive. I've never seen an instance where they have to the left positive or down positive. Sometimes books like to make the downward direction positive. That can be useful in some contexts, but not here. And so you see we're able to, also in the definition of the coordinate system, we're able to really define what a vector is, right? We're defining a vector as an object that's an arrow-like object that starts from the origin and has a tail at the origin, and its tip is at the location of the position. So you can imagine that really these dots are supposed to be shorthand for a bunch of different vectors that would start at the first location of the object and terminate or an end at the final location of the object. And so this figure here really should be several different vectors, all starting from the origin and ending at those dots. And you see here we also have some angles defining it. I mean, once you have a coordinate system, then you can start doing mathematics. I mean, you always do mathematics in physics when you have some sort of coordinate system or some sort of number system in place. That's really the building blocks. For most of these motion diagrams in chapters 1 and 2, it's only going to be a one-dimensional motion diagram, either vertical or horizontal or perhaps on an incline. Okay, and so that is the question we need to ask is, well, is position a physical measurement? And the answer, surprisingly, is no, because by this definition of position, the position depends on the coordinate system, and the coordinate system is always up to the experimenter, whether they want to put the coordinate system on the ground or on the ceiling or on one point or at the stop or the finish or wherever. But the thing that is physical is the displacement. And so the displacement is really our first physical quantity that we'll define in this chapter. It's defined as a vector difference between two positions at different time intervals. And so you see, when we're starting out, we're kind of defining all these terms all at once, and hopefully it's not too confusing with all the terms being thrown at you. But displacement really is the important thing. Oftentimes people will think that velocity is just position divided by time. It's technically displacement. And so to understand displacement, well, we need to know how vectors add and subtract, among other things. We'll be talking about the different operations that vectors take with each other as they're needed. So this chapter, we're only doing addition and subtraction. In the remaining chapters, we'll do scalar multiplication, and then eventually, when we need it, we'll do dot products and cross products and so forth. Okay, so what's vector addition? We have our little tactics box. Throughout the textbook, you'll find these tactics boxes, these model boxes. They're all really helpful. They're all really helpful to summarize all these things. So the first one is vector addition, adding B to add B to A. So look here, so seeing here we got vectors A and vectors B. Vector A kind of points up into the right. Vector B points kind of down into the right of relative size. B is relatively smaller. So this is the classic tip to tail method of adding vectors. So the first step is to draw vector A. And so you just click and drag it over there, right? And then here's the key part, where you place the tail of B on the tip of A. That's why it's called the tip to tail method. And then you create the triangle. You take the tail of, you draw a vector from the tail of A to the tip of B. So you kind of flip these terms here, and that vector connecting the starting point of A to the ending point of B, that is the sum. That's the vector sum of A and B. You could technically even write an arrow cap above A plus B, but it's the same thing. Incidentally, vector addition is commutative, just like the addition of real numbers, and unlike vector subtraction, actually. So that is the tactics box for drawing vectors and adding vectors. Well, that's not what displacement is. Displacement is the difference between two vectors. So how do we subtract two vectors? Well, what did we do when you learned subtraction to begin with? You know, besides borrowing stuff, I mean, you have to define the opposite. You have to define the opposite of an integer, or opposite of a natural number, right? Natural numbers 1, 2, 3, and so on. You define the opposite. So to us, that means symbolically, you just put a little dash in front of it, and then you define that opposite. Well, what is the opposite? The opposite of a natural number is the one that when you add to it, you get 0. Okay, 0 is kind of the identity for the integers. When you add it to it, you get the same thing. And so every natural number has its opposite, and then from that you can define the integers. Now we define, you do the same thing. We have to more or less define the opposite of a vector. So the opposite of a vector is the same length, but flipped 180 degrees. Or in more generally, so in 2 dimensions, it would be rotated 180 degrees. In 3 dimensions, you have to technically say that it's reflected about the origin. Reflection about the origin can sometimes be confusing, but that's what it is. So now again, to do A minus B, you start again with A, but now you have to add the opposite of B. So we add a negative B, and then that triangle creates A minus B, right? Incidentally, B minus A, just the same way in the integers, is not equal to B minus A is not equal to A minus B. And so this tactics box then summarizes vector subtraction. All right, this becomes, before we return to this last slide, let's just return to that displacement definition and now see that displacement between 2 positions is the final position, the one that's later in time, minus the initial position, the one that is further or more beginning in time. And it's always a vector that points from initial to final. And so you see here, we denote it by delta. If you're unaware that triangle is Greek letter delta, that's always going to be delta, and it's never by itself. It's always included with another quantity. So this delta vector R is literally read R final minus R initial, and it always points from initial to final. Well, what do we even mean by initial to final? You have to define a time interval, okay? What is time? Well, I'm not sure if we're going to be able to do that in this video, right? But suffice it to say, for our purposes, time is what we expect it is. It's what you measure with a stopwatch. You know, us in physics, we like to think about these deep ideas of what time actually is. I would, you know, be careful not to get too hung up on that and just talk about, you know, time in the context of what you're familiar with. If you get into Einstein's theory of relativity, you see that objects that are moving in time appear to be moving slower, relative to the objects to which they're moving. And then there's also the GPS system. So there's also fascinating things about time, but let's just stick with the basics of time interval. And for most problems, we'll just be sticking with standard seconds. That's the SI unit of time, which we'll talk about in a minute. But yeah, this summarizes the position, time, and displacement. These are the foundational quantities for everything we're building up to in this class, and especially in these few chapters. So in the next videos, we'll start to combine these quantities and relate displacement to really the central aspect of motion, which is velocity. So thanks for watching. We'll see you back here for the next video.